We continue our discussion of section 3.2, vector spaces. Last time we discussed the definition of a vector space. In short, a vector space is a non-empty set of objects. We call these objects vectors, on which we define two operations called addition and multiplication by scalars. This non-empty set of objects with two operations is a subject to the following 10 axioms. We split all these axioms into two groups. Group number one, axioms A and B. This set is closed under addition and multiplication by a scalar. Here's what we mean by that. Closed under addition means the following. If U and V are two objects from V, then their sum is necessarily from V again. Similarly is here. If U is an object from V, then Cu is an object from V again. Over here we have 8 remaining axioms. Commutativity, associativity. There is a unique element which is called the zero vector that satisfies the following property. U plus 0 is U. For each U, there is a unique vector negative U that satisfies this. U plus negative U is 0. And we have the remaining 4 properties. Last time, we also discussed example number 1. Rn is a vector space. What is Rn? Rn is the set of all matrix columns with n rows, where each component is a real number. So this n stands for the number of rows. R means each component is a real number. Let us generalize example number 1. In example number 1, we are talking about matrix columns. In this example, we have the set of all n by m matrices. Means instead of one column, we have m columns. Column number 1 and so on, column number m. Each component here is a real number again. So these are our objects, matrices with n rows and m columns. Now we define operations. Here's what we mean by U plus V. We add up the corresponding components. Done. Here's what we mean by Cu. We multiply each component by C. Done. So these are our objects. These are two operations. Once again, in order to define a vector space, number 1, we should define objects. Number 2, we should define two operations, addition and multiplication by a scalar. Here's what we need next. We have to define the zero vector and we have to define negative U for each U. After that, we show that our set with these two operations satisfy 10 axioms. Group number 1, closed under addition and multiplication by a scalar. Group number 2, the remaining 8 properties, commutativity, associativity, and so on. So this is example number 2 of a vector space, the set of all n by m matrices. Next example. One can show that R, the set of all real numbers, is a vector space again, which means real numbers with usual addition and multiplication by a scalar satisfies all 10 axioms. You may ask a question, what's the difference between R and R1? There is a little difference. R1 is the set of all 1 by 1 matrices. R is the set of all real numbers. Folks, think about questions here.
If you're talking about the set R, like what vectors would you use to define that set R?
The answer is, in R, vectors are real numbers. The number 1 is a vector. The number 2 is a vector. 0 is a vector. 1.5 is a vector. Each number is a vector. In Rn, the whole matrix is a vector. This is not a vector. This is not a vector. This matrix is a vector. In R, each number is a vector. In R, there are no matrices, numbers only. Each number is a vector. In Rn, there are no numbers. We have matrices only. Each matrix is a vector. This is not a vector. This is a vector. Does this answer your question?
Yes, sir. Thank you.
Next example. The set of all polynomials is a vector space, which means one can show that polynomials with usual addition and multiplication by a scalar satisfy all 10 axioms again. Because once again, polynomial plus polynomial is a polynomial. If we multiply a polynomial by a constant, it's a polynomial. Polynomials commute and so. By 0, we mean the number 0. The number 0 is a polynomial. So one can show that the set of all polynomials, which we denote by P, is a vector space. Now take a look at this. By Pn, we mean the set of all polynomials of degree at most n. And now this is important, at most n, which means, for example, P2 is the set of all polynomials of degree 2 and the set of all polynomials of degree 1 and the set of all polynomials of degree 0. Now, if you skip these two words, if instead of Pn, you consider the set of all polynomials of degree n, if n is greater than 0, this new set is not a vector space anymore. Here's why. Think about the set of all polynomials of degree, say, 2. The set of all polynomials of degree 2 is not a vector space. One of the reasons, there is no 0. Because 0 is a polynomial of degree 0. If we consider only polynomials of degree 2, there is no 0 here. Here there is 0. P2 is all polynomials of degree 2 and all polynomials of degree 1 and all polynomials of degree 0. However, once again, if we consider the set of all polynomials of degree 2, there is no 0 there. Therefore, this is not a vector space. Now, remember I said that if you consider the set of all polynomials of degree n, it is not a vector space if n is greater than 0. However, if n is equal to 0, it does not matter. We consider P0 or the set of all polynomials of degree 0. This is same thing, and therefore it's a vector space. P0 is equal to R. P0 is the set of all real numbers, which is a vector space. Folks, any questions here?
Can you explain again when you said the P2 and if it's equal to 0, then it's not a vector space?
Yes. So, according to this definition, P2 is the set of all polynomials of degree 2 and the set of all polynomials of degree 1 and the set of all polynomials of degree 0 because it's written at most n. So, Pn is a vector space. One can show that this is a vector space. One can show that Pn satisfies all 10 axioms. However, if instead of Pn you consider the set of all polynomials of degree and then skip these two words of degree n, if n is greater than 0, this is not a vector space. Simple example. If n is equal to 2, and if you consider all polynomials of degree not at most 2, but of degree 2, this set does not have 0, because 0 is not a polynomial of degree 2. It's a polynomial of degree 0. Does this make sense?
Yes, thank you.
Other questions?
If 0 is one of the coefficients, right, does that make it, would that then be in the vector space?
If I understand your question correctly, you say the following: 0 can be written as 0 times x squared plus 0 times x plus 0. Can we think about 0 as a polynomial of degree 2? Is this your question?
Yes, sir.
No, the answer is no. Here's why. Let us go back to pre-calculus and click on polynomials. Take a look at the definition. A polynomial function of degree n is this function where, and now over here, a n is not equal to 0. So degree of a polynomial is biggest power of x, where the coefficient in front of x to nth power is not equal to 0. So, despite the fact that 0 can be rewritten as 0 times x squared plus 0 times x plus 0, 0 is not a polynomial of degree 2 because the coefficient in front of x squared is 0. Does this answer your question?
Yes, sir. Thank you very much.
Here's another important remark. As I said, P0 is a subset of P1. P1 is a subset of P2. P2 is a subset of P3, and so on. However, going back to Rn, R1 is not a subset of R2. R2 is not a subset of R3, and so on. Here is why. R2 is not a subset of R3 because R2 consists of all matrix columns with 2 rows. R3 consists of all matrix columns with 3 rows. These are different things. So, once again, R2 is not a subset of R3, but P2 is a subset of P3. 2 other examples. The set of all real valued functions defined on R is a vector space. Real valued functions defined on R means function from R to R. Inputs are real numbers, outputs, values, are real numbers. By the way, this is a very important example. We will use it many times in this course. This set of all real valued functions is a vector space. And again, we prove that this is a vector space in the same fashion as before. We show that this set with usual operations of addition and multiplication by a scalar satisfies all 10 properties. Last example. Let us consider the following set. This set consists of only one vector, 0. Here is how we define addition and multiplication by a scalar. 0 plus 0 is 0, and c times 0 is 0. One can show that this is a vector space again. So, we are done with examples of vector spaces. These are most important examples of vector spaces. Folks, before we continue, can you think about questions?
So for a vector space to be scalar, so the addition of two numbers and the multiplication both have to be 0, right? I mean, on this example, yeah, where the cursor is right now, yes.
Give me a second. It's not just a scalar. As a particular case of this example, we can consider a set that consists of just one element, the real number 0.
Okay.
You cannot replace the real number 0 by the real number 1. If instead of boldface 0 you have 1, this is not a vector space because there is no 0, one of the reasons. Here, this is even a more general thing. By boldface 0, we mean an element that satisfies this and this.
Okay.
One can show that this is a vector space. In particular, if we consider the set that consists of one number, the number 0, this is a vector space.
Okay. Thank you.
So here, by boldface 0, we mean an abstract object that satisfies this and this.
Okay, so when it becomes 1, so it's not abstract anymore.
If instead of boldface 0, we have any non-zero real number, this is not a vector space anymore. One of the reasons in this set, there is no 0.
Okay, thank you.
Now let us discuss examples of sets that are not vector spaces. Example number 1. The set of all matrix columns with n rows where each component is non-negative. It is not a vector space. We show it in Appendix 1. Here it is. This set is not a vector space because of the following reason. This set is not closed under multiplication by a scalar. Indeed, consider this matrix column. This matrix column is from our set because each component is non-negative. However, if you multiply this by -1, now each component is negative and therefore it is not from B. By the way, compare this example with this one. Now, again, we consider the set of all matrix columns with n rows, where each component is strictly positive. We can show that this is not a vector space in the same way as before over here, or even easier, know that this set is not a vector space because there is no zero in this set. Zero is this matrix column. Here each component is zero. Zero is not strictly greater than zero, therefore this matrix column is not from this set, therefore this set is not a vector space. Next example. Over here, the set of all matrices of this form is not a vector space. One of the reasons, there is no zero in this set. There is no zero because the middle component is not equal to zero. It is 1. So we cannot write 0 in this way. To the contrast, if instead of 1 we put a 0, this set is a vector space, and we show it in Appendix 2. Moreover, we show it in 3 different ways. Way number 1, in order to show that this set is a vector space, we check all 10 properties. We show that it is closed under addition, multiplication by a scalar, commutativity, and so on. However, later today, I'll show you how to prove that this set is a vector space in a much shorter way. We will discuss it later today. So, once again, this set is not a vector space. This is a vector space. Example number 3. Let us consider the set of all triples of the form x, 0, x cubed. This is again not a vector space. Here's why. U1 is from this set. Indeed, if you replace x by 1 here and here, you will get 1, 0, 1. Similarly, U2 is from V again. Indeed, if you replace x here and here by 2, you will get 2, 0, 8. However, U1 plus U2 is not from V, so axiom A fails. First of all, U1 plus U2 is 3, 0, 9, because 1 plus 2 is 3, 0 plus 0 is 0, and 1 plus 8 is 9. However, this triple is not from V because it cannot be written as x, 0, x cubed. In fact, assume to the contrary that this can be written as this. In this case, x is equal to 3. But if x is equal to 3, x cubed is 27. But over here, instead of 27, we have 9. We got a contradiction. So this set is not a vector space again. Lastly, as we discussed, if n is greater than 0, the set of all polynomials of degree n is not a vector space because there is no 0 in such a set. Folks, before we continue, think about questions.
In the vector space with x1 and z, and it says it's not a vector space, could you explain that one more time?
Well, here this set is not a vector space because there is no zero. In order to come up with zero, we need 0 here, 0 here, and 0 here. We cannot come up with 0 because this is 1. To the contrast, 1 can show, and we show it in appendix 2, that this set, where instead of 1 we have 0, is a vector space. One way to show it is to check all 10 axioms. We do it over here. Was that your question?
Yes, but why does it need a 0 for it to be a vector
Because
space?
it's written over here. A vector space is a non-empty set of objects with 2 operations subject to 10 axioms. And axiom 3 says there is a unique element 0 called the 0 vector that satisfies this. If all our objects are of this form, we cannot come up with this because the middle element is non-zero, which means, remember, 0 satisfies the following property. We add 0 to any other vector, nothing changes. Note that if we add this vector to any other vector, because over here we have 1, the middle element will necessarily change. You see what I mean?
Yeah, thank you.
Okay, now let us continue. Let us go back to appendix 2. Once again, in appendix 2, I show that the set of all such matrices is a vector space. Solution number 1 is pretty long. We check all 10 axioms. However, solution 2 is much shorter. In solution 2, in order to show that this set is a vector space, we use Theorem 1. What is Theorem 1? Before we discuss Theorem 1, we need the following definition. A subspace of a vector space V is a subset H of V that satisfies 3 properties. Number 1, the 0 vector of V is in H. Number 2, H is closed under addition. Number 3, H is closed under multiplication by scalars. So, a subspace is a subset of a vector space V that satisfies these 3 properties. And now, question is it true that a subspace is a vector space by itself? The answer is yes. This is exactly what Theorem 1 says. A subspace is a vector space. Now, you can ask me the following question. How come that our subset satisfies only 3 properties out of 10 properties, and all of a sudden it is a vector space again? The answer is compare this definition and this definition. Over here, V is a non-empty set of objects. Over here, H is a subset of a vector space. This is a very powerful condition. Since H is a subset of a vector space, this guarantees that elements of H satisfy a bunch of properties from the list. Elements of H commute, elements of H enjoy associativity, elements of H satisfy all these properties because H is a subset of a vector space. What is left to check is axiom A, axiom B, and this. Because, let me give you a very simple example. Think about R. R is a vector space. But if H is the following subset, the set that consists of only one number, 1, this is a subset, but there is no 0 there. So, not every subset of a vector space is a space by itself. H, a subset of a vector space, is space by itself only if there is 0 there and if H is closed under addition and multiplication by a scalar. Here's why we need this and this. Again, think about R. And think about the following subset. All even numbers. Note that 0 is there. It's an even number. Moreover, H, the set of all even numbers, is closed under addition because even number plus even number is even number. However, it is not closed under multiplication by scalars. If you multiply, say, the number 2 by 1/3, the result is 2/3. It's not an even number anymore. It's not an integer. So, once again, a subspace of a vector space is a subset that satisfies these 3 properties, and theorem 1 says that a subspace of a vector space is a vector space by itself. This allows us to come up with shorter proofs in many cases. Let us go back to Appendix 2. Once again, one way to prove that this set is a vector space is to check all 10 properties. But here is a solution number 2. Observe that the set of all such matrices is a subset of R3, and R3 is a vector space. Now, 0 is from this set. If U is from H and V is from H, then U plus V is from H because we have 0 in the middle. Same for C times U. Conclusion: the set of all such matrices is a subspace of R3. Therefore, by theorem 1, it's a vector space by itself. Folks, any questions here?
Why do we need 0 as the middle term in every matrix?
Well, because if instead of 0 we have 1, this is not a vector space anymore. Because in such a set, and this set is over here, in this set, there is no 0. This is not a vector space. One of the reasons in this set there is no 0, because 0 is the following matrix: 0, 0, 0. This matrix is not in this set because here we have 1 in the middle. Was that your question?
Yes, I would also like to ask if instead of 0 you had like y, another variable, would that be in the set?
Good question. If we have x, y, z, this set is R3, which is a vector space.
Okay, thank you.
Let me give you another example. Let us go back to differential equations. Consider this homogeneous second order linear differential equation with constant coefficients. I claim that the set of all solutions of this differential equation is a vector space. Here is one. A solution of this differential equation is a real valued function. Therefore, the set of all solutions of such an equation is a subset of a no vector space. This vector space. Therefore, in order to prove that the set of all solutions of this equation is a vector space by itself, it is enough to check only three properties. It's exactly what we do here. Number one, is 0 in this set? The answer is yes, because x of t is equal to 0 is a solution of this equation. So 0 is from H. Number two, is it closed under addition? Yes, because we know, and let us go back to section 2.1. Over here, we prove that if y1 and y2 are solutions of this, and observe that this is a particular case of this. So over here we show that if y1 and y2 are solutions, then this is a solution again. In particular, if c1 is equal to 1 and c2 is equal to 2, y1 plus y2 is a solution. It's exactly what we are talking about here. If x1 is a solution and x2 is a solution, their sum is a solution. Similarly, if x is a solution, c times x is a solution. So, the set of all solutions of this equation is a subset of the vector space of all real valued functions defined on R. This set satisfies all three properties, therefore it's a subspace of the vector space of all real valued functions, and therefore by theorem 1 it's a vector space by itself. Folks, questions here?
Could you explain how number 2 applies to the given example?
So your question is why we need it or why this is true?
Why that is true for the example above.
Yes. So know that this equation is a particular case of this. Agree?
Yes, sir.
And note that in this section we showed that if y1 and y2 are solutions of that equation, are solutions of this equation, then c1 y1 plus c2 y2 is a solution again for any choice of c1 and c2. In particular, if we replace c1 by 1 and c2 by 1, this becomes y1 plus y2, correct?
Yeah.
So it's exactly what we do here. If x1 is a solution of this and x2 is a solution of this, according to what is written here, x1 plus x2 is a solution of this. Did I answer your question?
Oh, yeah, okay. I didn't know that it was referring to the solutions. Okay, that makes sense. Thank you.
Now, here is an important remark. The set of all solutions of this equation is a vector space because on the right hand side we have 0 and on the left hand side we have a linear operator. Now compare this example with this one. Again, on the right hand side we have 0, but the left hand side is not a linear operator because we have x squared. By the way, we've never discussed in this course how to solve such an equation. If you want, you can look at Appendix 3. In this appendix, I show you how to come up with this solution without guessing, but you don't really need it. Most important thing is, it is easy to check that 1 over t squared is a solution. You just replace x here and x here by 1 over t squared, take second derivative, simplify, you'll get 0. However, one can check that 2 times x, which is 2 over t squared, is not a solution of this equation. Again, if you replace x here and x here by 2 over t squared and simplify, you will not be able to get 0. So this is a solution. 2 times x is not a solution. Therefore, this set of all solutions of this differential equation is not closed under multiplication by a scalar. Therefore, the set of all solutions of this equation is not a vector space. Folks, any questions here?
So is this not true for non-homogeneous equations since you have that particular solution at the end?
Yes. If on the left-hand side we have a linear operator and on the right-hand side we do not have 0, the set of all solutions is not a vector space because there is no 0 in this set. Indeed, if the left-hand side is a linear operator, if you replace x by 0, L of 0 is 0. And therefore, if the right-hand side is not 0, 0 is not a solution. Was that your question?
Yes, sir. Thank you.
Now, let us go back to Appendix 2 once again. So, we just discussed solution 2. Solution 2 is much shorter than solution 1. However, take a look at solution 3. Solution 3 is even shorter than solution 2. However, in solution 3, we use theorem 2. What is theorem 2? Here it is. Consider several vectors, v1 and so on, vp. So, vectors v1 and so on, vp are from a vector space V. Theorem 2 says that the set of all their linear combinations is a subspace of V, and therefore, by theorem 1, is a vector space by itself. Well, question is, what is the set of all linear combinations? By a linear combination, we mean the following. We multiply V1 by some number, V2 by some number, and so on, Vp by some number. We add up the resulting u vectors. This is a linear combination. Here we are talking about the set of all possible linear combinations. In other words, over here we have a finite number of vectors, p vectors. Over here we have infinitely many vectors, all their linear combinations. In particular, if p is equal to 1, if over here we have just one vector v1, what is written here becomes c1 v1 only. There is nothing over here. So if we start with only one vector, we come up again with infinitely many linear combinations. These are all multiples of this vector. Repeat once again. Theorem 2 says that if we start with a finite number of vectors from a vector space V, the set of all their linear combinations is a subspace of V and therefore a vector space. Let us go back to this. Remember, in this example, we are talking about the following matrix columns, X, 0, Z. Know that any such matrix column can be rewritten as X times V1 plus Z times V2. V1 and V2 are vectors from R3, which is a vector space. What we see in front of us over here is the set of all their linear combinations. This is the set of all their linear combinations because there are no restrictions on X, there are no restrictions on Z. So these are all their linear combinations. But this is a vector space by Theorem 2. Therefore, this is a vector space. Similarly, take a look at this even simple example. Here's V1, here is V2. It immediately follows from Theorem 2 that the set of all their linear combinations is a vector space. Here's an example. Let us consider the set of all matrices of this form. Let us show that this is a vector space. Here's how we do it. Observe that any such a matrix can be rewritten as A times V1 plus B times V2 plus C times V3. Note that since A, B, and C are arbitrary scalars, this is the set of all linear combinations of V1, V2, V3, which are from the vector space R4. By Theorem 2, this is a vector space, therefore this is a vector space again. Folks, any questions here?
Why is V1 a vector space given it doesn't have a zero?
Are you talking about this V1?
No, the previous one. What, yeah, the 1, 2, 3 one. I mean, it doesn't have a zero. Why is it a vector space?
Well, good question. Note that I've never said that V1 is a vector space. I've never said that V2 is a vector space. V1 and V2 are vectors. These two vectors are from R2. R2 is a vector space. Since V1 and V2 are from a vector space R2, the set of all their linear combinations is a vector space by Theorem 2.
Thank you.
Other questions?
In the last example, where are you getting your zeros and ones and negative ones to multiply by, like the V1, V2, V3?
Well, just take a look at these explanations. Note that A minus B can be rewritten as 1 times A plus negative 1 times B plus 0 times C. Agree?
Yes, yes.
Similarly here, here, and here. And it's pretty obvious that this matrix column can be rewritten as A times V1 plus B times V2 plus C times V3. We just copy 1, 0, negative 1, 0. It's over here. Negative 1, 1, 0, 1 over here. 0, negative 1, 1, 0 over here. Was that your question?
Yes, and then since those are just like ones and zeros and negative ones, and that falls into the R4, the whole thing is a vector space?
Yes, the only thing that we need is the following. V1, V2, V3 are vectors from R4, and R4 is a vector space. Since what we see in front of us here is the set of all linear combinations of V1, V2, V3, by theorem 2, this is a vector space. Therefore, the set of all such matrices is a vector space. Once again, note that this is not one matrix. This is the set with infinitely many elements, because we can plug in any number instead of A, any number instead of B, any number instead of C. So here we have infinitely many elements. Here we have infinitely many elements. This set, the set of all such matrices, is equal to the set of all such matrices. This is a vector space, therefore this is a vector space. Did I answer your question?
Yes, thank you.
Other questions?
Professor, can you explain again why this represents all the linear combinations?
Great question. Here is the answer. Over here, A, B, and C are arbitrary scalars, which means we can plug in any number instead of A, any number instead of B, and any number instead of C. So these are all possibilities. We can plug in any number instead of A, any number instead of B, any number instead of C. This is A, V1, plus B, V2, plus C, V3. These are all linear combinations. There are no restrictions on A, B, and C. Was that a question?
Yes, thank you.